Here's the next question. Number 21. Consider a system consisting of a synchronous generator working at a lagging power factor, a synchronous motor working at an overexcited condition, and a directly grid-connected induction generator. Consider capacitor VAR to be a source and inductive VAR to be a sink of reactive power. Which one of the following statements is true? Let's go through the options given. Synchronous motor and synchronous generator are sources, and induction generator is a sink of reactive power. Second one says, synchronous motor and induction generator are sources, and synchronous generator is a sink of reactive power. Next, synchronous motor is a source, and induction generator and synchronous generator are sinks of reactive power. And all are sources of reactive power. Okay, so the first thing is, let's put it all into perspective by drawing out a figure. So consider a system consisting of a synchronous generator. Let me draw a very small diagram here. So we have generator working at a lagging power factor, a synchronous motor. Okay, then we have a motor here. And finally, we have an induction generator. Alright, so an induction generator, motor and generator all connected to each other. The conditions given in the question is the key. Okay, so since they are talking about VAR, let's call this as Q1, Q2 and Q3. Okay. Alright, now according to what's given in the question, the synchronous generator is working at lagging power factor. That is what is given here. Generator working at lagging power factor. What does that mean? It means that the generator operating at lagging power factor is in fact an inductive load should be connected. So an inductive load when connected makes the machine to generate reactive power to the lagging load. Alright, so that means that the reactive power be this way. Then we have the synchronous motor. Now the question says that the synchronous motor is overexcited. Now the condition when the synchronous motor is overexcited is it starts acting like a synchronous condenser. So I suggest you keep that in mind as well. It's a good point. Synchronous motor, when overexcited, acts as a synchronous condenser. Okay, and finally we have the induction generator. Now the induction generator over here, directly grid connected induction generator. Okay, so the induction generator will absorb the reactive power that has been developed in a magnetic field. Okay, so that means that we have both of these coming here, right? So this tells us that the synchronous motor and the synchronous generator, look at this node over here. Once you have determined exactly which way the VAR moves or the conditions for each machine given in the question, once you have the idea of what it represents, then you can say which ones are the sources and what constitutes the sink. Okay, let's go over this one more time. Generator operating at lagging power factor. So there is an inductive load is connected, which means that the machine will generate reactive power to that load. Then we have the synchronous motor which is overexcited, which acts as a synchronous condenser. And then the induction generator will absorb all of the reactive power that is developing. So this is absorbing. Now because it is absorbing, it is a sink. Okay, so the induction generator is a sink. You'll have to think of this in terms of just the English meaning as well of a sink. A sink is something that absorbs, something that it pulls in. So you will see from this figure here that Q1 and Q2 go through to Q3, which is absorbed into the induction generator. So synchronous motor and synchronous generators are the sources, while the induction generator turns out to be the sink in this situation. So the right option here is A. I hope this has helped. Here's the next question, number 22. A buck converter, as shown in the figure below, is working in steady state. The output voltage and the inductor current can be assumed to be ripple-free. Now the next figure shows the inductor voltage VL during a complete switching interval. Assuming all devices are ideal, find the duty cycle of the buck converter. Okay, so this is not a multiple choice question, so we will have to work it out. Now the first figure gives us the circuit for buck converter. And note the three different voltages over here. We have VG, the source voltage, VL, the voltage across the inductor, and V0 at the end. And this figure over here, the second figure, shows a waveform which gives us the inductor voltage VL during a complete switching interval, which means when the converter is on and when it is off. You will notice that the voltage range is from 30 volts to minus 20 volts. So we will have to keep that in mind while solving this. So let's start with the first part. We'll work on the figure over here given, the waveform given here. During the on period, let's write one equation, and during off period, we write another. So corresponding to the figure over here, let's write an equation during the on period. Now during the on period, the circuit is working. Just a simple explanation there. The circuit works during the on period. So during T on. Okay, let's write the KVL equation over here. So we have VG minus VL minus V0 is equal to 0. Quite a straightforward equation. Now, let's write this in terms of VL. Now, VL in terms of the rest, in fact. So we'll take everything else on the other side. So we have VL is equal to VG minus V0. Now we know from this waveform over here that VL during T on is 30. So this is 30 volts. So this is our first equation. VG minus V0 is equal to 30 volts. Let's call that number 1. Now the second equation is during the period of T off. Okay. Now during T off, what is off? That is what you'll have to just think. In simple terms, the source is off. So VG is 0. So we use the same equation here. So VL would be equal to 0 minus V0. So that gives us VL is equal to minus V0. Right? Okay. So this part during T off, VL is minus 20. And this further implies that minus V0 is equal to minus 20. And that gives us that V0 is equal to 20. So we can use V0 here and find out what is the value of VG using this equation over here. So VG minus V0 is 30. V0 is 20. So what will VG be? Let me just get another paper here. Okay. So the equation is Vg minus V0 is equal to 30. We know that V0 is 20 now. So that tells us that Vg is equal to 50 volts. Now because the question asks us about the duty cycle, here is a standard equation. V0 is equal to alpha Vg. Okay. Output voltage is equal to the product of the duty cycle times the source voltage. So this is the duty cycle. This is what we need to find. So we know what is the output voltage and we know what is Vg. Vg is 50 and V0 is 20. So that's 20 is equal to alpha times 50. Alpha equals 20 by 50, which gives us 2 by 5, and that's 0.5 0.4. So the final answer here is 0.4. Well, I hope this has helped. See you in the next video. Here's the next question, number 23. A steady state current of 100 amps is flowing through a power module. Here's the power module as shown in figure A. The VI characteristics of the IGBT and the diode are shown in B and C respectively. The conduction power loss in the power module in watts is. So again, this is not a multiple choice question and we will have to solve it. There seems to be a lot of information here, but you will have to pick the right one. So let's start with, okay, so we have here the power module given to us and the VI characteristics of both IGBT as well as the diode. Now because it is the steady state current of 100 amps, we will have to look at when the diode is conducting. Okay, so let's work on the VI characteristics of the diode over here. When diode is conducting, they have given us that dV by di is 0.01 ohms. So that tells you that this is the resistance value. Now we need to find out what is the voltage here. Okay, so when diode conducts, the figure C tells us that dV by di is equal to 0.01 ohms. Now we need to find out what is the voltage V. Now in general we know, well, from Ohm's law, that V is equal to IR. So we have R and we have the total current I. So let's put them together to find out what is V. 0.01 times 100. That gives us 1 volt. So we have the voltage, we have the resistance, okay, and we also have the moment here, the output voltage V0, which is 0.7 volts given according to this VI characteristics. So that will also help us, it will come in handy here, because the question says that we need to find out the conduction power loss. So the conduction power loss is 1, that's the voltage into current I plus V0 into current I. Now we cannot ignore the voltage that is given over here. So that's V times I plus V0 times I. So we have here 1, so that's voltage V, 1 into I, which is 100, so that's 100 plus V0 is 0.7, 0.7 into 100 is 70. That gives us 170 watt. So the conduction power loss or the total power loss is the losses here, that's 100 watts plus 70 watts, which gives us a total of 170 watts. I hope this has helped. Here's the next question, number 24. A 4-pole lap-connected, separately excited DC motor is drawing a steady current of 40 amps while running at 600 RPM. A good approximation for the wave shape of the current in armature conductor of the motor is given by. So this is a multiple choice. We have been given 4 choices of different waveforms. Now we have to choose the right waveform in order to determine the current in armature conductor. So let's begin with what's given to us, a 4-pole. So pole P is equal to 4. Now you see lap connected. Lap connected should tell you that the number of parallel paths is equal to the number of poles. So parallel paths is denoted by A. A is equal to 4. Okay. So the next thing given to us is the speed. Now we have been given that the speed is 600 RPM. Now let me tell you how to determine the time period. There are actually 2 ways by which we can find out the time period of a waveform. So before we go into that, let's find out what is the time taken to to complete one revolution. So it is given that the speed is 600 rpm. For 600 revolutions, it is 1 minute. So 60 seconds. How much would one revolution be for? So one revolution would give us a ratio of 60 by 600, which is 0.1 second. Okay, which means that for every one revolution, it takes 0.1 seconds. Now the total current in the question is 40 amps. So the total current is 40 amps, the current that is passing through, the steady state current. So since we have also been given the number of parallel paths, that is lap connected, now that should tell us that we need to find out the current in each parallel path. So the current in each parallel path would be the total current divided by the number of parallel paths, 40 by 4, which gives us 10 amps. Now because the current in each parallel path is 10 amps, that should tell us that option B is not the right one, because here it's given that there is a direct current of 40 amps. So that is wrong. Now the current in each parallel path is 10 amps, which leaves us with the options of A, C and D. Okay, the next is to find out the time period. Now you'll notice that in each of the waveforms, the x-axis denotes the time. So to find out the time period, we can use one of two methods. One method is to use the speed that is given to us and find out the time period through that. Or we can find out by calculating the pole pitch. Okay, so the pole pitch is the distance from center to center between two adjacent poles. It is good to keep a note of that as well. So we find out the time period for one pole pitch. In other words, it is the time period for one half wave or one half cycle. Sorry. Okay. So I'll show you both the methods. The first method over here is by taking speed into consideration. We have been given that the speed is 600. So we know the basic formula N is equal to 120 F by P. So from this, we can say that F is P times N divided by 120. The number of poles 4, N is 600 divided by 120, and to solve that, we get 20 Hertz. So if the frequency is 20 Hertz, we can calculate the total time period of one complete cycle. F is 1 by T. So T is 1 by F. So 1 by F is 1 by 20, which gives us 50 milliseconds. Now the next type is to calculate the pole pitch. For one pole pitch, the time period is time of one revolution divided by the number of poles. Now in the previous part, we found out the time of one revolution here. Let me just show that to you. Right, over here. One revolution is 60 by 600, which is 0.1 second. So, if we substitute the values here, T equals 0.1 divided by 4, that's 25 milliseconds. So, either you can find out the time period of one complete cycle or the time period of half a cycle. So, that's 50 milli and 25 milli. So, once you find out half a cycle, you can easily tell that one full cycle is twice this amount. Okay, so these are the two ways. Now, because you can find out the time period, it tells us that option A is also wrong. So we are left with options C and D. You will notice that each of the time periods is 50 across an entire cycle. So for linear commutation, this talks about DC motor, a separately excited DC motor. So for a separately excited DC motor, and that too for lap connected winding, you should know that the linear commutation and the change of current values from 10 amps to minus 10 amps is a straight line. So because it is a straight line, number C is the right option. I hope this has helped. Here is the next question, number 25. If an ideal transformer has an inductive load element at port 2, as shown in the figure below, the equivalent inductance at port 1 is. Okay, so here we are asked to find out the equivalent inductance at port 1. So we are shifting to the primary side. Now because the ratio given to us here is n is to 1. So which means that there are n number of turns here and 1 here. So that is the ratio, which clearly indicates that the primary side has got more number of turns than the secondary side. So if we are to shift the inductance from secondary to primary, now you should know that if the load element was shifted to the primary side, so here is the load, right? So it is shifted to the primary side through port 1. Now port 1 is the primary side. I told you because of the ratio given to us as n is to 1. Okay, so this means that the impedance will be high and the current will be low. So that is the ratio that you will have to remember as well. Impedance is high and the current is low. Just an important point for the primary side of an ideal transformer. So if the load element was shifted to the primary side, then the effective equivalent inductance, we will have to find out the effective equivalent inductance. Okay, so we need a relation between the ratio given over here as the number of turns to the inductance, the load inductance given over here. So if you recall, when the load element is shifted to the primary side, the effective equivalent impedance has a certain relation. So the effective equivalent impedance has the relation of ZL divided by NS by NP whole square. This is our load impedance, okay, while these are the number of turns of the primary and secondary. So if we were to apply the same logic for the equivalent inductance, we will get L, because that's the load inductance here, L divided by NS, the ratio is 1, and NP is the ratio N, 1 to N. So that's 1 by N whole square. So this gives us N square L. N square L matches option B. So for this question, the equivalent inductance at port 1 is N square L. Here's the next question, number 26. Candidates were asked to come to an interview with 3 pens each. Black, blue, green, and red were the permitted pen colors that the candidate could bring. The probability that a candidate comes with all 3 pens having the same color is dash. Okay, so this is a basic probability problem, and we can solve this by considering exactly what is given to us. Now it's given that we have 3 pens each. A candidate can bring 3 pens each. Now to find out the probability, the ratio is the possible events divided by total number of events. We need to find out each of these. So let's say that we have I have put down 3 boxes here, 1 box for each pen, since we have 3 pens here, 3 pens possible. So black, blue, green, and red. Now each candidate, let's take one candidate, me, or just any one candidate, will be able to bring. Now here for one pen it can be any one of the 4 colors, black, blue, green, or red. So there are a total of 4 possibilities of taking the first pen. The second pen will also have 4 possibilities. We can take either black, blue, green, or red again. So there are 4. And again there are 4 possibilities for choosing the color for pen 3. So altogether we have a total combination of 4 to the power 3. So this is the total number of events, the total possible number of pens or possible combinations in which a candidate can actually choose 4 to the power 3. So that is the total number of events. Now we need the possible events. Now the question says that the candidates were asked to come to an interview with 3 pens each. So the possibility is having the same color. So 3 pens. The probability that a candidate comes with all 3 pens having the same color, which means that we have 3 blacks, 3 blues, 3 greens and 3 reds. So how many possibilities? 4 possibilities. So possible events of the 3 pens having the same color. Is 4. So this is total. Okay, and the possible events of the 3 pens being the same color is 4. Either all the 3 are black, all the 3 are blue, all the 3 are green, or all the 3 are red. So now we can substitute both of this in the formula for probability. So the probability of this, let's call the event as A, would be equal to the possible events of the 3 pens having the same color divided by total number of possible events. So that's 4 power 3. That gives us 1 by 4 square, which is 1 by 16, and that's 0.0625. So here is the final answer. It's not multiple choice, so you would have to work it out. I hope this has helped. Here's the next question. Let S equals to summation n is equal to 0 to infinity n into alpha power n, where mod of alpha is less than 1. The value of alpha in the range from 0 to 1 such that S is equal to 2 alpha is dash. Okay, so basically we need to find out what is the value of alpha over here in this sequence. So we have the sequence given to us. S is equal to summation of n is equal to 0 to infinity n times alpha power n. Now it's given that S is equal to 2 alpha. So let's substitute that over here. 2 alpha is equal to summation n is equal to 0 to infinity n alpha power n. So now let's expand this and see what we get here. So we expand by putting 0, 1, 2, 3 and so on and so forth. So you will see that we get alpha plus 2 alpha square plus 3 alpha cube plus so on and so forth up to infinity. So let's take alpha common over here. We'll get alpha 1 plus 2 alpha plus 3 alpha square plus so on and so forth up to infinity. Now this expansion over here that is within the parenthesis, within the brackets, corresponds to 1 minus a to the power of minus 2. Now because this is alpha, it would be written as 1 minus alpha to the power of minus 2. That is only the part which is inside the bracket. 1 plus 2 alpha plus 3 alpha square, all that can be written as 1 minus, it's a binomial expansion. So 1 minus alpha to the power of minus 2. So this comes to alpha into 1 minus alpha minus 2, and this given that the condition mod of alpha is less than 1. So you will have to keep that in mind as well. So for mod of alpha is less than 1, it satisfies. Okay, so this is right. Alpha into 1 minus alpha to the power of minus 2. So this is 2 alpha. That's the left hand side. 2 alpha is equal to alpha times so much. So let's solve for alpha here. We'll get 1 minus alpha to the power of minus 2 is equal to 2, because alpha and alpha cancels out over here. Furthermore, alpha is equal to 1 minus 1 by root 2. How, you ask? Let me show that over here on the side. Please see. Now 1 minus alpha to the power of minus 2 is equal to 2. So this can be written as 1 divided by 1 minus alpha square is equal to 2. We can expand, write it in terms of a quadratic form, quadratic equation. Okay, so we'll get 1 divided by 1 minus alpha times 1 minus alpha is equal to 2. 1 is equal to 2 times 1 minus alpha into 1 minus alpha. 2 times 1 plus alpha square minus 2 alpha. 1 is equal to 2 plus 2 alpha square minus 4 alpha. So we now have a quadratic equation. Let me write this down here. 1 is equal to 2 plus 2 alpha square minus 4 alpha. So this gives us 2 alpha square minus 4 alpha minus 1 is equal to 0. So again we can find out what alpha is by using minus b plus or minus root of b square minus 4ac divided by 2a. You will see that you will get two values of alpha. Now you need to choose the value of alpha that lies between 0 and 1. That is the condition given in the question, the range of 0 to 1. So in this range, 1 minus 1 by root 2 is the value that you will obtain. I have written that here. So for 1 minus alpha to the power of minus 2 is equal to 2. When you solve this, you will get two values of alpha. Choose the value of alpha that comes within the range given in the question. Alpha lies between 0 to 1. And when we solve this even further, it comes around to 0.29. So alpha equals 0.29. This is the final answer. Now because it is not a multiple choice, we are to solve it entirely. Well, I hope this has helped. Here's the next question, number 28. Let the eigenvalues of a 2 by 2 matrix A be 1 and minus 2 with eigenvectors x1 and x2 respectively. Then the eigenvalues and eigenvectors of the matrix with the equation given as a square minus 3a plus 4i would respectively be. Okay, so we have our options. Now we are supposed to find out what are the eigenvalues and the eigenvectors of the given matrix. Okay, so we have been given that the matrix is a 2 by 2 matrix. So we'll put that down. So A is a 2 by 2 matrix. And the eigenvectors are given. Okay, so the eigenvectors are given as x1 and x2. And the eigenvalues are 1 and minus 2. So we'll put that down as well. The eigenvalues are 1 and minus 2. So let's assume that lambda 1 is 1 and lambda 2 is minus 2. The eigenvalues are usually denoted by lambdas, lambda 1, lambda 2 and so on and so forth. So for this matrix, a 2 by 2 matrix, lambda 1 is 1 and lambda 2 is minus 2. Now, because the eigenvalues are 1 and minus 2, it must satisfy the equation given there. So we have the equation as a square minus 3a plus 4i. That is the equation given. So before that, let's write down the eigenvectors of the given matrix A. Let us assume that they are x1 and x2. Okay, note that the given eigenvectors are x1 and x2, right? So they correspond to lambda 1 and lambda 2. You have to remember that as well. So let's now find out the eigenvalues of the equation given. So the eigenvalues of a square minus 3a plus 4i are, so it corresponds to both lambda 1 and lambda 2. So we can write this as lambda 1 square minus 3 lambda 1 plus 4i and lambda 2 square minus 3 lambda 2 plus 4i. Okay, so I is anyway 1 identity matrix. So we can ignore that. It's just lambda 1 square minus 3 lambda 1 plus 4 and lambda 2 square minus 3 lambda 2 plus 4. So these are the eigenvalues of the given equation of this matrix here. Okay. So the next thing we have to do is plug in the values 1 and minus 2 given to us. So we have here 1 square minus 3 times 1 plus 4 and minus 2 square minus 3 times minus 2 plus 4. So the eigenvalues are these two. We have the values of the given matrices 1 and minus 2. Substitute that in both the eigenvalues of the given matrix and you will find two different values. Now let us solve here. That's 1 minus 3 plus 4 equals 2. And here this is 4 plus 6 plus 4. That gives us 14. So the eigenvalues are 2 and 14 and the eigenvectors are x1 and x2. Now let's look at the options over here. We found 2 and 14, so 2 and 14 match and the eigenvectors are x1 and x2 which do not change. Therefore, option number A is the right answer. I hope this has helped. Here is the next question, number 30. Consider the following asymptotic Bode magnitude plot. Omega is in radians per second. Which one of the following transfer functions is best represented by the above Bode magnitude plot? Okay, so we have been given the magnitude plot, Bode magnitude plot, and we have been asked which of the four options is the right transfer function. Okay, so it is usually the other way around. We would be given a transfer function and asked to plot the Bode plot, but then here a twist. Okay, so before we get into how to identify which one of the four options is the right option, let's go into what a Bode plot actually is. So a Bode plot is the frequency response of a transfer function where one plot is the magnitude versus the logarithm and the other is the phase angle. So usually for a certain frequency we would have to determine both the magnitude as well as phase angle. But in this plot we have been given only the magnitude. Okay, so let me just write that down for you. Frequency response of a transfer function. Okay, so usually Bode plots can be drawn for both open loop as well as for closed loop systems, most commonly for open loop systems. And the standard form of what you need to remember or for the transfer function is that it would be in the form of 1 plus st1. You will notice that in the denominator all of these forms support. You have 1 plus st1 multiplied by 1 plus st2 and so on and so forth. You will find this form in the denominator. So we see that all the options have this form of denominator. So using the plot, let's try to find out which one is right. Now you will see here that we have a linear line here as well as a linear line here. Now these two are the slopes. Now the value given of this slope here is 20 decibels by decade and this one is minus 40 decibels by decade. And another point that you will have to remember is that for a Bode magnitude plot the slope would, the value usually starts from 20. It means that if there is a square in the term, if there is a square anywhere, either in the numerator or in the denominator, you will have to multiply it by the value 20. In the numerator, okay, here are some of the rules that you will have to remember, okay. So I'll put down the rule for the numerator as well as the denominator. The positive slope is always for the numerator, negative slope for the denominator. That actually helps, right? So we have the slope is positive for the numerator. And it always starts at 20. If there was a square term in the numerator, then it would be 2 times 20. So 2 times 20 is 40. So since the value here is 20, that means that we have a single term in the numerator which doesn't have a power. It's not raised to the power of 2 or so and so forth. Okay, so it starts with the value 20 decibels per decade. Okay, so this is the slope for the numerator. For the denominator, slope is negative for the denominator, and again you will have to think about the power of the factors over here. So the first factor doesn't have a power, it is single, so the value would be 20. But for the second one, it is times 2, which means that minus 20 times 2, which is minus 40. So this actually helps. Then you know that we can rule out option C and we can rule out option B, because it says minus 40, which means that it is minus 20 into 2. Minus 20 into 2. So that tells us that there is a squared term in the denominator, which means it can either be A or it can be D, one of these two. So that is clear. Now the next thing we need to know is, if you observe, here we have 0.5s, 0.25s, 2s and 4s. Quite a difference. Whole numbers, decimal numbers. So in order to check that, we can look at the frequencies over here. Now I have drawn I have put down 2 points over here, omega L and omega H. Omega L and omega H are known as corner frequencies. And the point at which the first slope comes at, 0.5 and 0.8, are supposed to be the frequencies at either ends. So the corner frequency will always be, the lower frequency will always be greater than the point given here on the plot, and omega H, or the second corner frequency, would be lesser than the point on the other side. So this is the general rule. Okay. So, and omega L and omega H usually have the form 1 plus S by omega. 1 plus S by omega. If you remember this form, it will be quite useful, because once you know 1 plus S by omega, that is 1 by omega times S. So here, if it is omega H is clearly lesser than 8. So take any value, just for an example, just to rule out which option could be wrong. So let's take that omega H is, say, 5. So that's 1 by 5. 1 by 5 is a decimal number. So all in all, we see that option A satisfies all of these rules and conditions. We have a square term which shows that this slope over here is negative and it is times 40. And we also see that since omega H is lesser than 8, it has to be somewhere, lesser than 8. Any value, you can take either 4 or 5 or 6 and determine it. And once you have that value, and because it is a negative slope, the form would be 1 plus S by omega. So 1 by omega, say for example 1 by 5 or 1 by 4, either way the value is a decimal value. So 1 by 4 will give us 0.25, which means that omega H is 4, and A would be the right option. I hope this has helped. Here's the next question, number 31. Consider the following state space representation of a linear time invariant system. So we have been given the state space representation over here. X dot t is equal to 1002 x of t. Y of t is equal to c transpose x of t. C is given to us, and the initial condition x of 0 is also given to us. We need to find out the value of y of t for t is equal to log 2 base e. So this is not a multiple choice question, so we will have to work it out and find the answer. So the first thing we have to do is, since we have been given the state space representation situation over here where x dot of t is 1002 into x of t. So let's take this matrix here. Since x dot t is given, so the first form that you have to remember is phi of t is equal to Laplace inverse of, now we have to find out the Laplace inverse, okay, so you should remember that, Si minus A, okay, so this can be written as Laplace inverse of 1 by Si minus A. Now A is the matrix here that we have been given, 1 0 0 2, 2 by 2 matrix. I is the identity matrix where all the elements are 1. So you can just assume I is 1. So S into I is 1. S into I is S. So it's S minus A. So you have to remember this form here, Laplace inverse. So let's apply this to the matrix given here. Okay. So here's what we have. We have Laplace inverse of, apply it to the non-zero elements. So we have 1 divided by S minus 1. Here A is 1. So S minus 1, 0, 0, 1 by S minus 2. Okay. So the Laplace inverse of 1 by S minus 1, you have to recall your formulas again. So here is where it helps if you have a sheet of all your formulas written down, so that when you're working out such problems, you can glance through. Oh, I'm not talking about the exam, I'm talking about when you're preparing. Okay, so have a sheet of formula right next to you, so that as often as you keep going through the formulas, that's how well you will be, you'll be thorough with. So here the Laplace inverse of 1 by 1 minus S is e power t. E power t. It's actually e power at. A is the value over here, 1. Okay, so that's 0, 0, and this is e power 2t because it is S minus 2. So here we have the Laplace transform. Now this corresponds to this equation right here. Now the next step is to calculate what is x of t. Now we have x dot t, we need to calculate what is x of t. So x of t is equal to phi of t, that's what we just found, okay, into the initial condition given to us. Where is that? Here, x of 0. So that's x of 0. Okay, so let's work that out. This is e power t 0, 0, e power 2t into initial condition 1, 1. So it is just basic multiplication of two matrices. Here we will have what x of t is, e power t, e power 2t. Now if x of t is this, we will have to find out the next step is y of t. Y of t is c transpose into x of t. Let me just grab another sheet of paper here. There. Okay, I'll just place it here so that you can see the question as well to review. Okay, so we have so far that x of t. Okay, so we have x of t. X of t is equal to e power t and e power 2t. That is our matrix. Okay, the next thing is to find out y of t. So y of t is equal to C transpose. So that is 1, 1 times x of t, e power t, e power 2t. Okay, C transpose is the transpose of this matrix. It is 1, 1, which is a row. You move it to a, 1, 1 is a column matrix. Therefore, we change it to a row matrix. That is the transpose of C. So that's 1, 1 times e power t and e power 2t. Let's solve this. We multiply and we get e power t plus e power 2t. So this is the equation for y of t. So we have now y of t is equal to e power t plus e power 2t. Just push that up here. Okay. Next, we need to find out what is the value of y of t when t is given to us. T is log 2 base e. So y at log 2 base e, wherever t is given, substitute log 2 base e. So that's log 2 base e plus e power 2 log 2 base e. Okay, here is where you have to recall your basic logarithmic formulas as well. 2 log 2 base e, 2 can be taken up and it becomes the power 2 square. So 2 square is 4. So we have here e log 2 base e plus e log 2 square base e. Okay, so first n log m is log m power n, right? And e to the power log n base e is n. So these are the general formulas that you will have to remember. And here we have 2 because it corresponds to this formula here, plus 2 square. 2 plus 4, 6. So our final answer here is 6. Well, I hope this has helped. Here's the next question, number 32. The loop transfer function of a feedback system is g of s h of s is equal to s plus 3 by s square into s minus 3. So this is our transfer function given to us. Take the Nyquist contour in the clockwise direction. Then the Nyquist plot of g of s h of s encircles minus 1 plus j0 once clockwise direction, twice in clockwise direction, once in anticlockwise and twice in anticlockwise. So this is going to take a while because we have to go through how to plot a Nyquist plot. We have been given an equation, a transfer function, and we need to find out the Nyquist plot. Okay, so before we go into the actual calculation, let's go over a few basic aspects. So Nyquist plot is another frequency response plot of a transfer function, and it's the basic is actually the same as Bode plot. Both plots are frequency response plots of transfer functions. Now the fact that Nyquist plot can be plotted for only open loop transfer function, while Bode plot can be used for both open loop as well as the closed loop. And to plot a Nyquist plot, we would have to find both magnitude as well as phase. Now that is important for any feedback system given to us. In order to plot perfectly the Nyquist plot or a Bode plot, we would have to find out the magnitude as well as the phase for a particular frequency given. So now for the Nyquist plot, we would need both magnitude and phase angle. We will go over both these calculations, and in order to plot the Nyquist plot, we need to determine the region where the plot needs to be drawn. Now the region is very important because the entire plane is S-plane. Okay, so you should know that the Nyquist plot would be drawn on an S-plane. So let's take this for example here. Now we have, this is the j omega axis and the entire plane is S-plane. Okay, so on the S-plane, the region of the plane that needs to be covered, or the Nyquist region, or so that's how it's called, we need to figure out which region covers the given transfer function. And also an important point is that we need to cover the region and avoid the poles and the zeros of the given transfer function. So I'll write that down over here. Need to cover the region of the S-plane where the system is to be evaluated, and we need to avoid the zeros and poles. So the zeros are the roots of the numerator. You should remember that. Zeros are the roots of the numerator and poles are the roots of the denominator. Okay, so look at the transfer function given to us. G of s, h of s is equal to s plus 3 s square into s minus 3. So this means that minus 3 is a 0. So we have here minus 3 is a 0, and for the denominator we have s square, which means that 0, 0. There are two poles over here and the third pole. So altogether 3 poles we have. 0, 0, 3. Okay, so we have 2 poles on the origin, so I'm going to write it over here. So we have 2 poles at the origin, 1 pole in the positive axis at 3 and 1 0 at minus 3. So basically we need to draw the Nyquist plot around the region in such a way that it avoids all of these 3 points here. It has to avoid 0, it has to avoid 3, and it has to avoid minus 3. Okay, so this is the general basics of how a Nyquist plot should be evaluated or drawn. Okay, so the next thing is that each of the s term given here must be replaced by j omega. Now by replacing j omega is when we evaluate the magnitude and the phase. So let's start with the magnitude calculation. So we start with magnitude calculation. Okay, so let me write down the transfer function. The transfer function is s plus 3 s square into s minus 3. Okay, so this is what has been given to us. Yes, okay. Now for the magnitude calculation. Okay, we start with replacing s with j omega. So we have here g of j omega. H of j omega is equal to j omega plus 3 divided by j omega square into j omega minus 3. Okay, so this is just the representation of s in terms of j omega. Now to find the magnitude, magnitude is mod of g j omega h j omega. The modulus represents magnitude, and okay, you know for the complex for a complex number a plus ib, the magnitude is root of a square plus b square. right? So we are going to apply the same thing over here. So we have, let's see, root of omega square plus 9 divided by omega square into omega square plus 9. This gives us 1 by omega square. Both of these get cancelled out. So the magnitude of the given transfer function feedback system is 1 by omega square. So in terms of direction, you have to remember a couple of points. One is that if the pole is closer to the origin, we move clockwise. But if a 0 is closer to the origin, we move anti-clockwise. But the question here, take a look at this rough diagram over here. We have 3, we have minus 3. Oh, don't consider the poles that are on the origin. So apart from that, you will have to consider the other pole and 0 that is given. Now you will notice that minus 3 and 3 are equally spaced from the origin, so we cannot tell which actually is closer to the origin in order to know which way we move. So if a pole is closer, then we move in the clockwise direction. If a 0 is closer, we move in the anti-clockwise direction. So in this case, the question already tells us that it moves in the clockwise direction. The Nyquist contour is in the clockwise direction, and we have also been given how it encircles. It encircles minus 1 plus j0. So let's just see how that works out. Okay, so we have the magnitude 1 by omega square. Next, let's find out the phase angle. So we have the phase angle to be calculated. Okay, so we start with the numerator. The numerator is s plus 3. So s plus 3 can be written as tan inverse of omega divided by 3. So this is our numerator. Minus, now we come to the denominator, s square. Now s square is j omega times j omega. So you should know that 1 by j omega can be considered as a whole half circle. So that's 180 degrees. So 1 by j omega square would be 180 plus 180. So that's a whole circle. 180 is 360, which means it's a whole circle. So one circle is complete, so we can actually ignore that. And then minus, what do we have here? We have s minus 3. So s minus 3 is written in as minus tan inverse of omega by 3. Now we evaluate this. As I said, that 180 plus 180 is 360, which means that for s square it completes an entire circle. So the phase angle would be written, evaluated as 2 tan inverse of omega by 3. We have tan inverse of omega by 3, minus and minus is plus. So we have 2 tan inverse. So now in terms of the transfer function, GH is equal to, can be written as magnitude and phase angle, right? So magnitude is 1 by omega square, phase angle of 2 tan inverse of omega by 3. So this is how the expression is written, magnitude and phase angle. Next we need to find out the values. In order to plot the Nyquist plot, we need to find out certain values. At omega is equal to 0, omega is equal to infinity, and since we have the pole and 0 at 3, let's find out omega at 3. Okay, so here we actually have pole at 3, so we find out omega at 3. So at each one of these values, let's find out the entire expression. So at omega is equal to 0, substitute 0 over here, 1 by 0, let's call it's infinity. At angle 2 tan inverse of, substitute 0 here, so 0 by 3, anyway the whole thing is 0. So that's our first value. Next, at omega equals to infinity, substitute infinity here, we will have 0 and the angle being 180. Okay, 2 tan inverse of infinity by 3. So at omega is equal to 3, we substitute that over here, that's 1 divided by 9 omega square, and the angle being 2 tan inverse of 3 by 3, which is 1. So I guess I can write that out for you here. 2 tan inverse of 1, and that would be 1 by 9 times 2 into 30. So that is 1 by 9 angle 60 degree. Oh, I'm sorry. No. 45. 45. So tan inverse of 1 is 45, and that gives us 90 degrees. 1 by 9 to 90 degrees. Okay, so this tells us a whole lot. We have the phase angles of 0, 180 and 90. So the values of omega we have taken 0, 3 to infinity. So this tells us that the plot starts from 0 and it goes to 180 through 90. So I'll draw that here. So it sort of resembles something like a very weird shape like so, and it goes as an entire circle this way, comes here. So that is a very rough diagram of the plot. So we have omega is equal to 0 here, omega is equal to 0, and omega is equal to infinity here. Okay, and this entire circle is this region over here, that's minus 1 plus j0. Minus 1 plus j0. That is the, see, that's what the question says. It encircles minus 1 plus j0. So that's here. Okay. So what that actually tells us is that it starts at 0 and it goes to 180 through 90. And because it circles in the clockwise direction, it goes this way and then it goes to 180 through 90. So you have to remember that. It goes like so, like so, like so, and then it comes back to the point where it starts off. Okay, and you should also know that since there are two poles on the origin, we have two poles on the origin over here, right? 0, 0. So because there are two poles on the origin, we will have two semicircles. Two semicircles with radius of infinity. Now you have to remember that. Okay, so two semicircles of radius of infinity, and they mirror each other. So they are symmetric. Alright, so they are symmetric, and the direction, it starts from 0 and it goes in the clockwise direction, and because it is symmetric, it stops. The flow of the plot actually stops where it starts, which means that it takes only one, it encircles only once, it cannot encircle again. Now because there are mirror images of the radius omega is equal to infinity, it will go just once, and that means A is our right option. It circles once around minus 1 plus j omega 0 in the clockwise direction. Well, I hope this notes is enough to give you a basic understanding of what a Nyquist plot is, or how it can be plotted using the transfer function given to us. Well, I hope this helps. Here's the next question, number 33. Given the following polynomial equation, s cube plus 5.5s square plus 8.5s plus 3 is equal to 0. The number of roots of the polynomial which have real parts strictly less than minus 1 is. Okay, so when the question says have real parts strictly less than minus 1, it's talking about s is equal to minus 1 plane. Okay, so that's the first thing you need to know. If the value is given, they are talking about s is equal to minus 1 plane. And strictly less than the given value indicates that they are looking for the roots that lie on the left half of the s is equal to minus 1 plane. Okay, so keep this in mind, the roots that lie on the left half. Now, the equation given, the highest power of this polynomial is 3. Now because the power is 3, it means that there are a total of 3 roots. Total number of roots, 3. Out of the 3, we need to know how many lie on the left, and the rest would obviously lie on the right. So the first step is, let's write down the polynomial given to us, s cube plus 5.5s square plus 8.5s plus 3 is equal to 0. Now because the value is given as minus 1, we need to replace s with s minus 1. So that's the first step, replacing s with s minus 1 into this equation. So wherever we have s, just plug in s minus 1. So that's s minus 1 cube plus 5.5 s minus 1 square plus 8.5 s minus 1 plus 3 is equal to 0. Now you have to expand this entire equation and it has to result back into a polynomial of s power cube form. So let's do that. Now s minus 1 whole cube is s cube minus 1 minus 3s square plus 3s plus 5.5 into s square plus 1 minus 2s plus 8.5s minus 8.5 plus 3 is equal to 0. Simplifying further, plus 3s plus 5.5s square. Better yet, let's directly write down, take common terms out. I think that would be easier. Let's do that instead. Okay, so we have s cube plus, taking s square common, that's minus 3 plus 5.5 plus s into 3 plus 8.5 minus, so that would be 11 plus, we'll write down the constants in the last brackets, 5.5 minus 8.5 plus 3 is equal to 0. So that's s cube plus 2.5s square plus, that comes around to 0.5 s minus, okay, what do we have here? That's 5.5 minus 8.5, and that's okay, so it comes to 1 is equal to 0. Okay, so this is our resulting polynomial equation. Now that we have this equation, in order to find out how many roots lie on the right half and how many lie on the left, we will have to take Routh-Hurwitz table. We will have to find Routh-Hurwitz table. I'm assuming that you are already familiar with this, but either way we will go through it step by step. So the name is Routh-Hurwitz. So that's basically RH table. Let me write down the equation. Polynomial s cube. Okay, we got it. S cube plus 2.5s square plus 0.5s minus 1 is equal to 0. So the first step of forming the RH table is to write down the powers of s in order here. So we have s cube, s square, s, and the constant corresponds to s to the power of 0. Now if the first power of s is even, then the first row of values will contain the coefficients of even powers. But because over here we have s power 3 as the highest, 3 is odd number. So the first row of elements, the first row of values will contain the coefficients of the odd powers of s. So the coefficient of s power 3 in the equation is 1. This is even, then this is odd. So we go back to this s power 1. The coefficient of s power 1 is 0.5. So we write 0.5 here and that's it. Now next row, we have s square here. So s square is an even power, square is an even power. So we look at the even powers of s, starting with 2.5. 2.5 is the coefficient and the next coefficient is minus 1. Okay, so we have all the coefficients written out in this form. Now we will have to find out the others in the table. Now we have already worked on this. There is nothing else on the third column over here, so we can completely ignore that. We can directly go to S, the first element in this row here. So this is something like what we do when we find the determinant of a matrix. What we do here is 2.5 multiplied by 0.5. Always remember to move from left to the right. 2.5 into 0.5 minus 1 into 1 divided by the first number here. Okay, so you have to remember that. Always divided by the first number here. So I'll write it down on this side here. So that's 2.5 into 0.5 minus 1 into minus 1 divided by 2.5. If we solve this, I believe that would be 0.9. 2.5 into 0.5 is 1.25 plus 1 divided by 2.5. 0.9. So 0.9 goes here. Okay, now the next is, in order to find this element, we need a third column here. Now because we don't have a third column here, we will assume that this number is 0. You can just write it as 0. That's about it. Okay. Next, we go to the s naught term, s power of 0. And to solve this, we use the same procedure here, but this time we use these 4 values here, these 4 elements. And that would be 0.9 multiplied by minus 1 minus 0 multiplied by 2.5 divided by 0.9. So I'll write that here. So we have 0.9 multiplied by minus 1 minus 0 times 2.5 divided by 0.9. I should have written just 0 there, but either way. So we have here minus 0.9 divided by 0.9, which is minus 1. So the value here is minus 1. S power 0 is minus 1. Now you will have to look at, we don't have to find anything here, because again, in order to find the second term in this row, we would need a third column terms. So assume that it is just 0. Anyway, once we have formed this table, the table is complete. Look at the first column. Now when you look at the first column, you will see that the first 3 terms are positive and the final term is negative. You have one change of sign from here, that's positive to positive, positive to positive, positive to negative. So in the first column, we have a single one sign change. And because we have one sign change, it means that there is one root on the right hand side, on the right half of the plane. Now if one root lies on the right half of the plane, that immediately tells us that there are 2 roots left out of the 3. So total 3, 1 lies on the right half, which means that the other 2 The other two roots lie on the left half of the plane. Left half of s is equal to -1 plane. And that is exactly what the question asks of us. It asks us about which the number of roots that lie strictly less than -1. Left half, which is 2. Well, I hope this has helped. Here's the next question, number 34. Suppose x1 of t and x2 of t have the Fourier transforms as shown below. x1 of t corresponding to x1 of omega and x2 of t corresponding to x2 of omega. You should know that the axes are actually j omega. Okay? So, which one of the following statements is true? x1 of t and x2 of t are complex. x1 of t and x into x2 of t are also complex with non-zero imaginary parts. Okay, so basically here, all of the options deal with either x1 of t and x2 of t are real or complex, and the multiplication of both is real or not. Okay, let's check it out now. The first thing is notice both the waveforms given to you. The Fourier transforms of x1 of t is x1 of omega, j omega, and the second one is the Fourier transform of x2 of omega. Okay, look at the waveform over here. You will see that if you flip this over, you will arrive at this. Right? Okay. So the first thing is, if you flip this over, just flip the right hand side to the left hand side to the right hand side, it's not symmetric. Now because it is not symmetric, it is a complex signal. x1 is a complex signal. I'll write it down over here. x1 of omega and x2 of omega, they are not conjugate symmetric. Now the reason they are not conjugate symmetric is that's just it. If you just flip the function around, flip the waveform around, you will see that it is not symmetric. If you get the exact same waveform, if you flip it over, then it is known as conjugate symmetric. In mathematical terms, f of minus x should be equal to f of x. When this is obtained, it is conjugate symmetric. Because it is not, f of minus x is not equal to f of x, that is x of here, okay, these two, when they are flipped over, they are not conjugate symmetric. So therefore the signal will not be real. Now because the signal is not real, that tells us, okay, here, I think I'll write it down over here. Or better yet, let me get another sheet of paper. If you'll just give me a quick second. Yes, okay. So I'll write it down here, or better yet, underneath the waveforms given to us. Okay, so J1 of omega and, I'm sorry, X1 of omega and X2 of omega are not conjugate symmetric. Again, I repeat that it is symmetric only when f of minus x is equal to f of x. Only then it is conjugate symmetric. So this means that the signal or the signals x1 of t and x2 of t are not real, and if they are not real, they are obviously complex. x1 of t and x2 of t are complex. So that's the first part. Then the next part is they want to find out about the multiplication. The multiplication of both signals x1 of t times x2 of t. Now for Fourier transform, now because the question tells us specifically that it is based on Fourier transform. Now the Fourier transform of x1 of t into x2 of t would be 1 by 2 pi times the two forms given here, x1 of j omega, x2 of j omega. This is multiplication, please note. So that's 1 by 2 pi into this. And by looking, we can tell that these two, that the multiplication of both will be conjugate symmetry. Think about it. If you multiply both of these waveforms, just club them together. If you club them together, you will see that they indeed are conjugate symmetric. They are symmetric. Each part, that is the left hand side and the right hand side, will be symmetric with each other, and that indicates now, because x1 of omega into x2 of omega, it's this portion over here, this portion is conjugate symmetry. Conjugate symmetric. Okay, you should know that just the waveforms by themselves, okay, I think, yeah, now it's in view. Okay, so just the waveforms by themselves, x1 omega and x2 omega by themselves separately, they are not conjugate symmetric, but if you club them both together, multiply them both together, you will notice that the waveforms are indeed conjugate symmetry. And because they are conjugate symmetry, its counterpart of x1t into x2t is also conjugate symmetry. And we noted that if it is conjugate symmetry, that means that it is real, which means that x1 of t times x2 of t is real. So we established this fact, x1 of t into x2 of t is real, and x1 of t and x2 of t separately are complex. So let's see which option. Here, option number C, x1 of t and x2 of t are complex, x1 of t into x2 of t is real. Well, I hope this quick analyzation of the forms, waveforms and the notes help. Here's the next question, number 35. The output of a continuous time, linear time invariant system is denoted by t into x of t, where x of t is shown as the input signal. A signal z of t is called eigensignal of the system t. When t into z of t equals gamma z of t, please note that's a gamma, where gamma is a complex number in general and is called an eigenvalue of t. Suppose the impulse response of the system t is real and even, which of the following statements is true? Now the key here is to note that it says real and even. The impulse response of the system t is real and even. And the options given talk about cos of t and sine of t being eigensignals and their corresponding eigenvalues. So in this case, what we have to do is first examine what kind of system it is, and the fact that it is even and real and even. And then we have to note what happens when we get cos of t, when we assume that cos of t is the input signal, and what happens when we take sine of t as an input signal. Okay, so let me just get a sheet of paper. Okay, so we begin with what's given, the impulse response. Now the question says that the impulse response is real and even. Now, if it is real and even, that indicates that h of j omega is also real and even. Now, h of j omega is the complex term given in the question. The question says that gamma is the complex number, right? So, since gamma is the complex number, take h of j omega, which is also real and even. Now, in the previous question, we looked at what when a system is actually called real. It is a real system. I'm sorry. Let me just write that again. A signal is called real when f of minus x equals f of x, and that indicates that it is conjugate symmetric. Okay, so only when it is conjugate symmetric will we say that the signal is real. And because h of j omega is real, since the impulse response is real, we can say that h of j omega is equal to h of minus j omega. You see the relation there? That means that it is conjugate symmetric, which in turn shows that it is real. Okay, so now let's assume that here we have a system, linear time invariant system. There is a certain input and we obtain a certain output. Now, in terms of complex, we can write the input of x of t in terms of e, so that would be e power j omega naught t, and we obtain as the output h j omega naught into e power j omega naught t. Okay, so since this is real and even, that means that if we were to take the same system, LTI system, the same system with an input of e power minus j omega naught t, then the output response would be h of minus j omega naught times e power minus j omega naught t. Okay, so here you will have to note that h of j omega naught equals h of minus j omega naught. That's because that it is real. Again, reiterating that fact, which means that that is the point that should give you, should lead you to the solution, to find the right answer. Okay, so now we have to evaluate what happens when the input is cos t and what happens when the input is sin t. So let's start with cos t. Now cos t is the input. So you will have to recall how cos t is written. Now cos t is written in terms of e as e power jt plus e power minus jt divided by 2. Now this is the input, okay? So if we pass this signal in the LTI, this is what we obtain. Now in regards to this, let's write the output. So the output would now be h of j times e power jt plus h of j e power minus jt divided by 2. Exactly the same. Now let's take h of j out as a common term. Now if we take this out as a common term, we get e power jt plus e power minus jt divided by 2, and that leaves us with h of j times cos t, because this is again the input cos t, and that gives us hj cos t. Note that the output given in the question is exactly this form, gamma times z of t. Gamma is our complex number into z of t, which in the question is the input, and the input here we have considered as cos of t. Okay, so that means that satisfies. Now let us check with sine. Okay, so we have worked out with cos, now it is time for sine. Okay, so let's take the input as sine of t. Now, the expansion of sine of t in terms of e is e power jt minus e power minus jt divided by 2j. You should note that the denominator has the complex term 2j. Okay, so if we give this as the input this time, what happens to the output? Now, the output would be h of j times e power jt minus h of minus j e power minus jt minus divided by 2j. Let's take h of j common here. Okay, so we will obtain e power jt minus e power minus jt divided by 2j. Okay, we can consider this as h of j, fine, not a problem. So here we have h of j times sine t, because it is exactly same as the input. So this tells us that both sine t and cos t satisfy the system given. Here it says that the signal z of t is called the eigensignal of the system. Now we have taken two eigensignals, both of cos t and sine t, and we have seen that the output is the output corresponds to what is already given here, gamma, which is a complex number times the input. So this means that both sine t and cos t are eigensignals and they have the same eigenvalues. So that corresponds to option D here. Cos t and sine t are both eigensignals with identical eigenvalues. I hope this has helped.